All right, so where do we start? First of all, let's talk about field. Right? We know field, unlike particles, field are spread out. Right? There is, uh, we know there is electrical field, magnetic field, but there is also pressure field, temperature field. Field is a concept that a physical entity that is spread out all over the space. So it is pretty abstract. I think in classical physics, field, this concept field is abstract enough. Now we're going to quantize it, and it will become even more abstract. So what I would like to do first is to start with a material metaphor of fields to help us have a better, a more concrete, solid picture of what field is. And when we quantize it, we will have a better, I don't know, mental image of what quantization means for fields. All right. So the best, so we know fields are like this. Fields. So this is like very much like Einstein's space-time, right? Curvatures stuff. But let's just imagine this fabric. It's called field, and it's spread all over the space. Okay. And let me just call it electromagnetic field. We'll explain what this. I assume that a lot of you have knowledge on electromagnetic fields, but just bear with me. I want to just build everything up from the foundation. Okay, so this is what fields look like, and the closest material metaphor I can think of is a spring mattress. So what a spring mattress is, so we know you have a bed, right? A bed look like this. This is a very ugly looking bed, but you have spring. What I show here is 1D, but in 2D you have rows and columns of springs, right? And sometimes these springs are connected. So let me just draw each spring. I represent each spring as a dot, as a circle. Okay, so these are springs, and they hold the bed in the direction normal to this board. Okay, so they do this. All right, and a lot of times the springs are connected with using other springs, or even you can think of the bed as a connecting point, like offers the connections, because each spring is attached to the bed, right? The mattress. Oh, sorry, this whole thing is the mattress. But you can imagine that the top layer is working as a coupling mechanism. So these springs, these individual springs, are coupled together. Okay. Now, before we couple them, let's say each spring has a resonant frequency, a natural frequency at omega naught. So they oscillate at omega naught. Now, due to the coupling, so let me just write kappa. Due to the coupling between them, let's focus on this two first. Due to the coupling between them, the oscillation frequency changes. Okay? And the way they oscillate also changes. Let me just use a 1D picture to illustrate. So let me focus on this direction. This is X and this is Y. Let me focus on the X direction. Okay? Due to the spring that connects both kappa, the resonant frequency becomes different, and you can say it's almost like an energy splitting. So you have one mode that looks like this, and the other mode that is slightly higher. Okay, and this is probably kappa over m, something like that. Okay, M is the mass of the spring. Okay. Now, when they are connected, they no longer oscillate as individual springs. They oscillate as an entity. And they can do this. They can do two kinds of oscillation. One is this. The other is this. The Brevin mode, the center of mass mode. This or this. They oscillate as an entity. Okay, and this corresponds to this. This corresponds to this. Okay. When you have more springs, you can imagine that this process will just continue, keep on, and will split into more and more different frequencies. These frequencies are called mode. This we call mode, okay? And so, and the number of frequency that is available in the mode correspond to the number of the degree of freedoms in your system. In this particular case, okay, we assume that in this particular case, we assume that each spring as an oscillator is a 1D oscillator oscillating at omega resonant frequency omega naught, and this oscillator at frequency omega naught. So there are 2 degree of freedoms, 2x, right? And when the spring couple, then they split into also 2 frequencies. So if you have 9 spring, so if this is these are all 1D and you have 9 of them, all connected. Okay. Oh, this is not. Let me just write. I think this is better. Okay. Okay. So this is omega. Okay. So geometrically, this works better. When they are all connected, you can imagine that there are 9 frequencies. So this is 2 frequency. They are going to be 9 frequencies. And there will be 9 different modes. Yeah? Why do I talk about mode? Because when we talk about mode, we are no longer concerned with individual oscillators. The mode becomes the physical entity. And it is the mode that is real. Yeah? The individual springs sort of lose their individual identity, and they all become a component of a bigger thing, and that bigger thing is called mode. Okay. For the field, we have very similar situations. Okay. Let's imagine that we have also in space x1, y1, x2, y2, x3, y3. We have in space many individual oscillators per se, and they are all connected somehow. Okay, and so when one of them is perturbed, it represents a part of the body that is perturbed. So it's really the body being perturbed locally. However, it is the body being perturbed, so the entire body will start to oscillate. Yeah? Okay. So that's as far as I can go with this metaphor. So just imagine there are fields or so when we talk about field, we are working at this mode, this sort of for materials, it is collective motion. It's called collective motion. But here for fields, we don't use that language. We don't say that it is collective motion. we just simply say that they oscillate as an entity, entire complete entity, and and yeah, and it's called mode. All right, so we're working at this level. Okay. Now, the particular field that we are interested in is called the electromagnetic field. Okay. Why does it call electromagnetic field? Why do I call it electromagnetic field? Some of you might think, oh, this is apparently a vector potential. So why don't you just call it vector potential? Well, the reason is, according to Maxwell's equation, we have, so like we all heard about Maxwell's equation, right? But we need to know one very important thing. It is not only a set of equations. It delivers a very important message. And that message are electric field and magnetic fields, they are not independent. Before Maxwell, everybody thinks electric field is by its own one thing, and magnetic field is by its own another thing. They are not related, just like we think gravity and electromagnetism are not connected. Maybe one day they will be. We don't know. A lot of people try to do that. But before Maxwell, electric field and magnetic field are disconnected concept. Until Maxwell's came along, and then he gave a set of equations that reveals that reveals the connection between electric field and magnetic field. So you see, the first thing you notice is that this set of equations are kind of symmetric for electric field and for magnetic field, right? It is the curl product, it is the dot product and the curl product that matters. That's the first thing. So on the left-hand side, you have a pretty symmetric correspondence, okay? On the other hand, on the right-hand side, besides the material terms, which is the charge and the current, besides the material terms, they also look pretty symmetric. Okay? So we have a partial derivative here, we have a partial derivative here, right? So Maxwell reveals through his equation that electric field and magnetic fields are two sides of one coin, two sides of the same coin, okay? And that same coin is called the electromagnetic field, okay? Let me just write it down. Through this equation, you can derive this relation. Oh, sorry. Okay, they are two different sides of the same coin. You see, this is a temporal derivative, and this is a spatial derivative. And that coin is the electromagnetic field. When you take the spatial derivative of the electromagnetic field, did I say spatial? When you take the spatial derivative of the electromagnetic field, you get a magnetic field. When you take the temporal derivative, you get an electric field. Okay, so they're really one side of the same coin. So when we describe electromagnetic field, we can just use, we don't need to use the two sides. We can just use that coin, okay? Electromagnetic field, okay? And by the way, I talk about oscillators, right? So what correspond to this individual oscillator at each time, at each point is a vector, okay? So it's a vector, and the vector has three components. So it's really like three oscillator in one. Okay, and it can oscillate in this direction or this direction and this direction. The direction of the oscillation called the polarization. Okay, and the oscillation amplitude can change too. Okay, so yeah. Okay, so that's what Maxwell tells us. This is, let me just write it down. Electromagnetic field, and this is electric field, and this is magnetic field. Okay, and when the electromagnetic field oscillate, it also oscillate in different frequency, just like our mechanical mode. They also oscillate in different frequency, and when they oscillate in a particular frequency, all local oscillators oscillate in that particular frequency. Okay, and this can have and the field can and and the field can so like I said, the field can oscillate in different frequency, but it can also oscillate in a superposition of many frequencies. Okay? Just like this, you can have a superposition between omega 1 and omega 2, right? When you have an arbitrary, like when you give it an arbitrary push, right, like a pulse, like this, both motions, omega 1 and omega 2, will be excited. So you see, it oscillates in a superposition of two frequencies. All right. Now, the reason we're trying to draw a kind of analogy between the mechanical field and the electromagnetic field is because the following. So before the quantization of electromagnetic field, people already have learned how to quantize matters. Okay, they know what to do with atoms. They know what to do with electrons. They know about matter waves. Schrodinger equations has already been developed, and so people know how to do quantum mechanics. But when it comes to material, when it comes to field, since it's a very different thing from particle, in particle we have Newton's equations, right? In field we have Maxwell equation. We don't have Newton's equation. We have Maxwell equation, and these two equations are basically unrelated in the classical realm. So people have already learned these tricks, all these condensation tricks for Newton's equation for particles, but they don't know what to do with field, which is governed by Maxwell's equation. So what happened is they kind of have to guess. And so when you read a books on any books on quantization of field, quantum field theory, quantum optics, you might feel like it's kind of ad hoc. A lot of steps are not derived. They are just given, and for some reason it works. So you might be puzzled. I am too. I was too. When I first learned about the subject, I was very puzzled. Right? So what we're gonna do today is we want to try to make that transition as smooth as possible. But note that this is by no means a derivation. This is just something that help you to kind of process this information in a more logical way. Okay. After all, physics is a guessed work. You cannot derive physics, unlike mathematics. With mathematics, you start with certain axioms, and then you derive an entire set of mathematics according to this few principle or these few axioms. When you change your axiom, which is allowed, you can just change it. You can go from Euler geometry to Riemann geometry, right? Just by changing the axioms, by like how to define the angle of a triangle. You can derive like a whole another set of mathematics. But physics is different. Physics is about guesswork. We try to understand nature, and nature doesn't always or never work according to our will. So we have to guess how it works. And people make different guesses. Some guesses are close and some guesses are far. And that's the best we can do. We try to make guesses. And hopefully one of our guesses are close enough that it will make sensible predictions. And we kind of just use that as a basis, and then we iterate this process, and we continue to modify our assumptions and our guesses. All right. So I just want to start with this disclaimer that quantum optics is guessed. Nobody know how to do quantization of fields. They just guessed, and they just happen to work. All right. But let's see if we can make this transition easier for us. So like I said, let me not use particle because it's kind of confusing since we have wave-particle duality. Let me just use matter. Matter. So we already learned that the quantization of matter requires two ingredients. The first ingredient is you change the dynamical variable into operator. Okay, so what are the dynamical variables we're talking about? For a ping pong ball, or sorry, a baseball. For baseball, the dynamical variables will be x and its momentum, p, right? So basically position and velocity. So these are the dynamical variables, what we use to describe. These are the physical variables of this object, and we use this to describe this object. The state or the value of these variables describe this object, right? But now, quantum mechanics says we cannot use the dynamical variables to directly describe the object. We need to kind of separate things. Okay, let me just say it. So they become operators. They become operators, but operator needs to operate some things, right? So what are the things that the operator operates on? Turns out it is what it operates on is a probability wave function. Okay, so it operates on a probability wave function. Very much like in the differential equation, you have certain operator like derivative, integral, curl product, or dot product. Those are operators, and they operate on a certain function, right? So functional calculus, like so that kind of things. So people found that this operator needs to operate on the probability wave. Therefore, we replace the notion of ballistic motion to probability wave function. So we use a function to describe that wave. It's pretty much like a field function, a field, okay? And we replace the notion of probability motion to probability wave. And this probability wave kind of describes the state. This describes the state of the object. So instead of using the dynamical variable to describe the state, now we need to use it. Now we need to change it to an operator. Okay, and when the operator operates on a state, it gives different operator. So it's okay. So different operator operate. So let me just use. Okay, let me just use this. Right. It's like the operator inquire information from the wave function, and then this will give you the state value on x, and the state value on p. Okay. All right. So we have kind of we need to break the description of the motion of matters into two parts: the operator and the wave function. And through this inquiry process, we can obtain the physical information that we need to make a measurement, to compare with our measurement. So that's how. So this is basically how it works for matters, and people found that this recipe does work. Okay. This recipe does work. However, to find a mathematical equation that put together this operator and the wave functions, we need to change Newton's equation, which is F equal to ma, we need to change Newton's equation into Hamilton's equation. Okay, Hamilton equation is basically just another form of Newton's equation, a different way of formalized it. Okay, Hamilton's equation is this. Okay. The reason we need to change to Hamilton's equation is because in Newton's equation, it is not easy to see what is the constant of motion. You don't see that here. You don't see that here, the constant motion, right? When you have an oscillator, what is the constant motion? Is it position? No, the position changes all the time. Is it velocity or momentum? No, momentum changes all the time. Okay. Is it kinetic energy? No, kinetic energy also changes. So everything changes with time. But there's one thing that remains the same throughout the entire motion, and that is the total energy. Okay, so that's this thing that does not change with time becomes the starting point of quantum mechanics. Okay, and so instead of focusing on how the dynamical variables changes with time, we need to, people have learned that we need to actually focus on the constant motion, and that is the energy, which is the Hamiltonian, and that is this. Okay, so later on, people consider Hamilton equation is probably a more basic, a more fundamental formalism of classical mechanics than Newton's equation. Okay, and starting from here, people start to apply this quantization procedures. They just change all the dynamical variables into operators. Yeah. And then it takes a very special person, his name is Schrödinger, to find a set of equation for this. Okay. An equation that connect the operator with the probability wave. So that is Schrödinger's contribution. He found how to connect the operator with the probability wave. Let me just write this. Okay. Well, you might wonder, okay, then what is the use of Hamilton equation? Is it lose its fundamental kind of is it no longer fundamental in physics? That just doesn't make sense, because if it's fundamental if it's a fundamental equation in classical physics, then where is it in quantum mechanics, in the quantum realm, right? In nature, there's in college, we teach classical physics in one course and quantum mechanics in another course, but that nature doesn't work that way, right? They don't have different course number for quantum mechanics and classical mechanics. They all work at the same time. It's just a matter of which realm you're in, right? So there's this transition. So I don't know if you have this question, but it kind of puzzled me, like, if this plays a fundamental role in classical physics, like where is it in quantum mechanics? You don't see any resemblance between Schrödinger equation and this, right? Well, it turns out that if we want to restrict ourselves to only these dynamical variables without involving the wave, the probability wave function, it is still possible to formulate to get a formalism for quantum mechanics, and it's called Heisenberg's equation. So this is as simple as this. You just basically change everything to dynamical variable. Okay? So this is called Heisenberg equation. Heisenberg's. Am I spelling this right? B-R-G? Guys, Heisenberg. Is it spelled as B-R-G? Heisenberg's equation. Okay? So it turns out that quantum mechanics can indeed be formalized in terms of just the dynamical variables, and it's called the Heisenberg equation. And later it was proved the Heisenberg equation and quantum and Schrödinger equations are equivalent. Yeah. So so it does. So Hamilton's equation does remain a fundamental. Does remain of its fundamental importance in quantum mechanics, and it just has another name called Heisenberg's equation, and this is equivalent to Schrödinger's equation. However, because the mental, the picture, and since these are all operators, we can no longer imagine these are dynamical variables for the object, right? So if we want to have something if we want to develop a mental picture, then we need to use the wave function, the probability wave. That's easier. Okay. All right. So this is quantization for matter. What about quantization for fields? How do we do that? Okay. So this, what I'm gonna tell you next is it's kind of Wayne's special, and you won't hear anything. You won't hear this anywhere else. So pay attention. So let's start with. So this is matter, and here we have field. Precisely, we have electromagnetic field. Let's focus on electromagnetic field. Okay. So the lessons we learned from quantization of matter is that we need to change the dynamical variables to operators, and it is the constant of motion that matters. Okay, so why don't we start with the constant motion? What is the constant motion? Constant motion is basically the energy, right? So for fields, the energy is this. Right? You have the electric energy, you have the magnetic energy. But really, there's only one field. So this energy can also can be described just by that only. Okay, how do I get this? Well, we know that E is equal to this, right? So in terms of unit, this is A times a frequency. Okay, so let me just write it in terms of unit. E naught is equal to this times a frequency times A. Okay, some kind of frequency. Yep. And B is the spatial derivative. So B naught is some kind of 1 over length. We call that wave vectors. Okay, so just some kind of wave vector. Right? All right, so if we replace this by this, you have the energy described by the field, right? Now, if this frequency and this wave vector, or this 1 over length, whatever this is, if they are related, as in electromagnetic wave, if they are related, provided this relationship, okay, then, oh, by the way, let me just do one thing first to show you how this is implied, kind of hinted. Mu is, we know that epsilon and mu is 1 over c squared. Correct? So what you do here is, look, see, these are, like I said before, this is a guesswork, right? So you kind of follow some hints, some clue, and you try to put together a picture. So this is what we're trying to do. We're trying to guess. Okay, so this is not like a very rigorous math, but we're just trying to make an educated guess. So mu is that, so it can be replaced by epsilon times c squared, right? Yeah, okay. And you see these two parameters, they can be grouped together, okay? And this is the same as that, right? So if there is a connection between this frequency and this wave vector, then it will be very convenient. You'll be very convenient because this just becomes, what is it? It just becomes this. Yeah? Okay. And that's omega square a square. Not a omega square a square. Okay, sorry about this factor of 2. Okay. Okay, so as I said, the electromagnetic field is the more fundamental field to be used. So the electromagnetic field energy, although it has 2 terms, it should really be just 1 term. Okay, well, this is a very important hint for us. So for people who are really familiar with quantum mechanics, might recall that, so maybe I'll write here. My recall this similarity between this and the mechanical oscillator. In the mechanical oscillator, we have E equal to, let's see, we have x squared and 2np squared, right? So recall that the Hamiltonian for matter is a potential and p squared. So if we want to look for anything that is similar to this form, then we go to a mechanical oscillator because the potential is quadratic. It has the same dependence as p here, right? And in so this is a mechanical oscillator. To quantize it, to make it a quantum or classical, oscillator, classical oscillator. To make it a quantum oscillator, like I said, we follow this procedure, change the dynamical variables into operators. Okay? And then what we do is if you're familiar with let me just say x squared and y squared. If you're familiar with complex algebras, when you see this, immediately you will think, oh, this is just the norm of a complex number, right? So if I have this as the real part and this y as the imaginary part, this is just the complex number times its conjugate. Yeah. So classically, this is equivalent to this. Let me put everything here. X plus I to M. Okay. Probably need a bigger board. P. Yep. Okay. So this is true. Okay. So can we do it here? Can we do it here? Okay, let's try to do that here. I will tell you why we want to do this in a minute. Okay. The reason we kind of want to do this is because we want to try to find the operator for energy. Yes, the operator is a sum of this energy operator, Hamiltonian, is the sum of two operators, x squared and p squared, and they separately act on the wave function, right? But nevertheless, none of them are constant motion. This is not constant motion. This is not constant of motion. So when they act on the wave function, they changes with time, right? X squared changes with time, p squared changes with time, yeah? If we can just find an operator, like a single operator for the energy, perhaps that energy operator, when it acts on the wave function, it will not change, that thing, whatever the outcome is, it will not change with time. Okay, so motivated by that, we are looking for a single operator that describe the energy. Okay, that is why we kind of prefer instead of x and y two variables, we prefer one variable. And the price to pay is to make that variable needs to be complex. But that's okay. Okay? So this is the motivation, right? But however, we know that the operators, if you know a little bit about linear algebra, you know that operators, functions can be represented by a column vector. Okay, so it's all its values, all its possible values can be represented in the column vector, and the operator, like the derivative and integral, whatever operate on that function, can be represented by a matrix. Okay, so the matrix connects the vectors, the input vector to the output vectors, right? So with that in mind, with that background knowledge in mind, we know that the operator are like matrix, and matrix do not commute. So this expansion doesn't really work. Okay, this expansion doesn't really work. When these are numbers, classical dynamical variable, when they are numbers, you have the cross term like xp and px. And with numbers, you don't have this communication problem. So here, actually, there is a minus sign. So I is a minus sign between, and they just cancel each other. But with matrix, things are not simple, are not as simple. There's potentially this problem with commutation. Okay? So similar with, if you expand this, you will see a term that looks like this. And we cannot just throw this away. Potentially, this is not, very likely this does not commute. Most matrix A does not commute with matrix B. This just in general, they are not commuting. If there are special matrix, maybe they do, but in general, they don't. Okay? So we expect that commutate operator do not commute. So this expansion isn't really true. Okay? But can we make it work? That's the question. Can we make it work? And the answer is yes, we can make it work. And so there are something you can do about this term we call the commutator. There are something you can do about the commutator, and you can make this work. You can still find the Hamiltonian, the operator for the energy operator. You can still do that. But let me not do it with the classical mechanics. Let me just do that with electromagnetic field, because this is a more direct connection. I mean, I can do it here, and then we will have to draw analogy. Why don't I just do it here? It's the same thing, right? Okay, but people have shown with matter that this does work. So we're gonna follow their footstep and do the same thing with the electromagnetic field, and see if that trick will work. What the trick works for the harmonic oscillator, which has the same functional form as the electromagnetic field. So we want to see if the trick also works for that. Okay? So, why don't we take a short break, 5-minute break, because this is like a 2-page thing. All right, let's get started. All right, so for the sake of completeness, I'm starting again with the classical energy, which had two terms. And these two terms, we're motivated to split them into a product of complex numbers, right? All right, so we have known this, and we motivate this with the mechanical oscillator because we know this is what works. So we try to do the same thing. And what happens next is that we're supposed to put a head on every dynamical variable and turn it into operators. Okay? Before I do that, sorry, just for the sake of simplicity of the derivation, I want to just factor out the dimensions from the operator. So I want to make my operator dimensionless. So all the units are here in this parameter. Okay, B, E naught, and B naught. So these all represent the unit. And E and E operate, E head and B head, they represent the electric field operator, and this represent the magnetic field operator. Okay, so just with that, according to the recipe of canonical quantization, we're motivated to just change everything into operators, right? However, like I said, when we change to operator, this is not necessarily true. This equality is not necessarily true. Okay, so this could become a different thing from this. You see what I'm saying? So putting the operator here, and putting operator here. If you put operators on both sides of the equation, the equality is no longer, it's unlikely to hold. Okay? So that's why we want to just make a note for ourselves that this operator, when we change this to the operator form, this is not necessarily the original operator we're looking for. Okay, nevertheless, we're motivated to try this. So we try and see what happened. Okay? And when you try that, and after the expansion, you see this, right? This is what we want. This is that, right? We want this. This is good. We want this. Okay? But this extra things we don't want. All right? So the difference between the equality here will hold if we can try to get rid of this thing. Yeah? And the best way to get rid of it is, of course, make the commutator 0. That would be the easiest. Okay? If we make it to 0, that would be the easiest. Just hold on. If we make it 0, that would be the easiest. But there's a great danger in that, because not many operators, not many metrics are supposed to commute. They commute under special conditions. Okay, so can we do what's the next best thing we can do? We want to get rid of this operator. We don't want it to be an operator. Okay, so the next best thing we can do is turn this into a number. Turn this entire term into a number. If we can make it into a number, that is also good. It's just like a constant following my operator, and life is still good, right? Because a number is basically a unit operator, right? So that's harmless. So 0, yeah, it is great if I can have like $1 billion. If I can be a billionaire, I will have all the funds I need to do my research, right?
But if I cannot be a billionaire, well, maybe the next best thing is for me is to get is to be is a millionaire. That's also good, right? So instead of just restrict this to zero, that's like a very very strong condition. Let's go to the next best thing. Let's make it into a number, which is an identity operator. Let's make it into a number. Make this turn into a number. And because this is a real operator, right? This is a complex number, complex op. So these are real operator. This is our real operator, but this term is a complex operator. This term is a complex operator. You have the complex and the complex conjugate. So this is a real operator. So real operator means all its coefficients should be real. Okay? If you have a matrix form for the operator, all matrix elements should be real. That's what real operator means. Okay? So this is obviously a real operator. So should the other side of the equation, right? This apparently is a real operator. Okay? So what number should we make this to be a real operator? Well, we have this I here, right? The minimum thing we can do is just to get rid of this I. Yeah? And remember I told you the operator that we choose is dimensionless, right? So we basically just need to choose one number that makes this I go away. Okay? What's the simplest thing you can think of? I, or better, minus I. Right? Because that just kind of neutralize, like take the trace out of this entire thing. You don't even change the sign. Okay, a minus I. That would be a very natural choice. Okay? Minus 5i minus 2i, that's all too much. Like this is the minimum thing you need to do to make this work. Unfortunately, nature also appreciates this simplicity, and it goes with this. Nature goes with the simplest way to go about things. Okay, so let's make this minus I, and that's and we'll see what happens. Okay, so if we make this minus I, then this sorry. Okay, this just becomes a term, a constant, sort of, and this becomes this is the original Hamiltonian, the original energy operator we would like to get, right? So therefore, we see that this operator that we are after is this particular form minus a constant. Okay? Minus a constant. Now, we want to use this connection because we are after we're looking for a single operator. We're looking for a single operator that can give us that represent this, right? So this is this operator, this energy after canonical condensation, it contains two operators. We are really at what we are after is a single operator that can represent this, okay? And now we found this very nice relationship, okay? And so if we can find a single operator that represents this, then that will effectively give, that is effectively the operator of A. Yeah? Yeah, right? Because I said that this is through the connection of the plane wave, okay? Through the connection of the plane wave, we can describe the electromagnetic field energy in terms of just the A, right? And now we're looking for a single operator that represents the energy operator, okay? If we can find that single operator is basically the operator for A, okay? I hope you see the connection. Okay, so presumably we want to do is to have let me
I'm sorry, did you miss part 2 on the epsilon on the second last row?
You mean here?
The first term.
Here? Square?
To the right. So square the epsilon.
Oh, yes. Thank you.
Okay.
Yes, I do. Yes, thank you. I think this takes a long time, but believe me, this is worthwhile. I've tried to read so many quantum optics textbooks, and none of them make sense. But if you have this, it will all make sense to you. So, well, it depends on if you want to have a more advanced studies in this subject. If you do, then what we're doing here will be very valuable to you. Okay, so let's come back. Let's come back to this original Hamiltonian. Okay, let me just call this 1. Okay, and let me call this 2. Okay, so the original Hamiltonian. The original Hamiltonian now is this entire thing minus this term. And just to save time, okay, no worries. We'll just do it step by step. Okay, and minus C E. right? Okay, so what we want to do is to cast this into a form that have a single operator. And here we kind of have done it. Yes? Here we kind of have done it. This is a single operator. We can call this A squared. We can call this, or let me just call it this. Okay? And this is A. Okay? So we kind of have it. Yeah? What we need to do next is to clean up the parameter a little bit, right? So here we have the unit of B, we have the unit of E naught, and we have C, we have epsilon naught. We have like four things.
It will be A star, right? A dagger should have like transpose also.
Sorry?
It should just be A instead of A dagger A star, right? Complex conjugate.
No, this is an operator.
So, but it will have like A star is
Yeah. But this is real. Remember, this is a real operator. As we define here, these are real operators. So the E star, sure, you can put E star here, but it's the same thing.
I mean like,
this is the same as this, okay? Because E is the same operator. The E and B, they are real operators, okay? So, but I don't want to overcomplicate things. All right, I want to focus on the logic. Yeah, but yes, you're right. We should have put this here, but I don't want to do it. Okay, so let me erase this. Okay. All right. So there are four parameters here. E naught, epsilon naught, E naught, B naught, and C, right? It would be nice if we can clean up the parameter a little bit and see if we can have a more sensible form of this, right? And motivated by our earlier discussions on this is equal to the, this is described by a single electromagnetic field. If we make the connection between omega and C through the plane wave assumption, right? So here we can try to do the same thing. Again, the plane wave. But here, plane wave assumption. And plane wave assumption, besides this connection between omega naught and K naught, there's also a connection between B and E. Okay? So let's use that, and then we can turn OB into E. And this will give us a very nice looking a very clean form of okay, doesn't it look nice? It cleans up quite a bit, right? And this also is dimensionless. Yeah, this is dimensionless. So let me just call it A and A dagger. Okay. And you can see that this is the energy. right? This is just an energy term. This is just an energy term. So you have the energy term, right? So like what we want a single operator that represent the actions of the energy operator, and we've done it. Yep. So that's kind of nice. Okay. And we could. So what about this connect? What about this A? So this A is not really. So if we want to. So if we want to find the operator for the A, we could also do that at this point. Okay, because we know that E naught is omega times A naught, right? So if we define our A operator, so the canonical transformation. So using this. Okay, so this is a canonical quantization. Sorry. So instead of equality, I should probably use an arrow. That is more appropriate. Okay. So this is also an arrow. Then we will see that this is let me see. Here we have epsilon naught, omega 0, A0, right? Okay. And all right, now you see okay, wait a minute. Wait. Yeah. I think it's better to do it here. Okay, it's better to do it here. Okay. So you see, it will be natural to identify this as the electromagnetic operator. Right? So basically this is saying, this implies that A, the electromagnetic operator, capital A, is this small case A that we find here. And that is a combination of the electric field operator and the magnetic field operator. So the electromagnetic field operator has its real part as the electric field operator, and its imaginary part as the magnetic field operator. So this is the relation we are after. This also reflects the physical reality that electric field and magnetic field are two sides of the same coin. Now we see how they are indeed the two sides of the same coin, because at the quantum level, in the quantum regime, the electric field operator is the real part of this, and B field is the imaginary part of this. So they are just really like inseparable. The electric field and magnetic field are really inseparable entities. Yeah. Okay, great. So having identified this, we can now say that this is it'll make sense to write this as okay. Yeah, and this is the okay. All right. And
if you take capital A,
and now give me a minute. Let me finish. All right, and now it will be so effectively we have found the operator corresponding to this in terms of E and B, right? We know they are connected, but we don't know how they connected quantum mechanically. Now we found it. Yeah. Okay. The last thing is, well, what about this energy operator? Is this the energy operator we're after? Well, it is very tempting to stop here and say this is the energy operator we're after, right? But I don't know about you, but this minus sign looks, because I think plus sign is the natural sign that should be used in all physics equations. If there's a minus sign, something's going on, like there's extra things going on, okay? So I don't like this minus sign. I want to get rid of it. I want to see if I can get rid of it, okay? And so like I said, everything is guesswork. And I'm just trying to motivate my next move with a reasonable rational. Okay, so can I get rid of it?
Sorry, in the last part you wrote, should the omega be squared as well?
Oh, here? I'm missing a square. Okay, thanks. All right. So now I have identified the electromagnetic field operator is small case A. I'm just gonna use this. I'm gonna stick with this, okay? Because this is more consistent with the language that people use in the textbook, okay? So I'm just gonna call, because here I didn't give it a name, right? Now I'm going to give it a name. Electromagnetic operator. is, so that is A,
Small case A.
electric, oh, sorry, field operator. Electric field operator. Magnetic field operator. Okay, so these are the operators are the field operators are all dimensionless. Now, remember, this is this plus that. Okay, it's pretty straightforward, very easy to remember. And this is, just remember, E is the real part, and the B is the imaginary part. Okay. Now, I want to get rid of this minus sign. Okay. So I want to see if there's something I can, some trick I can play. Okay. Know that earlier we have defined in this process, we have defined this commutation relationship, right? So using this, we can find a commutation relationship of this. Okay? And what is that? Let's try to see. E, B, E minus B. Okay. Okay. Oh, you know what? This is too complicated. This is stupid. I'm sorry. This is not elegant. A better way is this. Okay. And if you have learned anything about commutator or linear algebra, this should not be a difficult. So first of all, you know this is 0, right? You know EE and BB are 0. The operator commute with itself, of course. Yeah. And so this. So we just use this distributions rules, right? So we have the cross term plus IBE. Yeah? So this minus EB and this plus BE. Okay? Now we have this. If BE commutator is minus I, then EB will be plus I, right? Oh,
I'm sorry, there's something I missed. I want to okay, give me a second. Hi. I just realized that you see this 2 here. This 2 here is annoying. It's a bit annoying because this classical energy, this is supposed to be just epsilon omega naught A squared, right? So this 2 here is a little bit annoying. Okay. So I want to put them into a bracket and make the part of the operators. Okay. So I'm gonna do it here. So instead of so this will go in here and here. So instead of A equal to E and B, I'm gonna make it like this, almost like an equal superposition. Okay, you can interpret it this way. I have a half-half equal superposition, right? I normalize it. So this is a unit operator, right? Okay, so I've done that. So I changed my definition. And if I change the definition, then this becomes, the 2 goes away. The 2 is absorbed into A. And here's a 2, right? The 2 goes away. The 2 goes away. Yep. Okay, so let me write this. Okay. Okay, good. So what I need to change here is I need to add a factor of 1/2. Yeah? So this is 1/2. This is 1/2. And this is minus 2i half. This is 2i half. Okay? You see there's a lot of back and forth because I'm guessing. I'm trying to make everything looks as natural as possible. But we're getting there. All right, so this is, according to this is plus I, this is minus I. So here you have a plus I, you have 1/2. And here you have minus I, you also have 1/2. Okay? Together they give 1. Okay? Together they give 1. Okay, the reason I want to do this is because my purpose is to get rid of this constant. My purpose is to get rid of, sorry, not this constant, this minus sign. Okay? And I know that so this is a product, right? So a lot of times a product is associated with commutators. Okay? And I know my A is a real operator. Sorry, A is a complex. Okay, never mind.
So a lot of times this is associated with commutators. So I'm just thinking, okay, maybe by using this commutation relation, I can somehow manage to change the sign. So that is what motivated me to calculate the commutator for A. And because I've defined the commutator for B and E, I can of course calculate the commutator for A and E and A dagger, and I found that this is actually it has a very simple formula, just equal to 1. It's even simpler than this. Okay, and this is also how you can see this is a more fundamental field operator, because it's simpler. Okay, as paraphrasing Dirac, simplicity is, or symmetry is the beauty of physics. The beauty and simplicity and the elegancy is the guiding principle of physics equations. So this definitely looks nicer than this. And that also signified why A is a more fundamental field operator to be used in field quantization. Okay, so what we learned in classical electromagnetism is that A, it doesn't really matter. It's just like a vector potential, and we seldomly use it. But its importance is really just revealed here in the quantization of the field. Okay, so I want you to take note of that. All right. So if we have this relation, then therefore our H bar is A dagger minus, right? This is what we had.
Do we need capital A0 since we are using small a?
Yeah, we're using small a now. Okay. Yeah, I'm using capital A here just as like an intermediate step to rationalize the correspondence. But here now we're clear that small a is the electromagnetic field operator. There's no doubt about it. So we're gonna use that from now on. This is equal. So using the commutator relation, a dagger is equal 1 plus a dagger a. Okay, so you have 1 on one hand, you have minus half on the other hand. So this gives you this. Okay. Now it looks much nicer, right? Minus sign is gone. And the price to pay is just to switch the order between A and A dagger. And that's, I'm happy to do that. There's no harm. Okay? So it looks like this is the energy operator we're after. Precisely, this term times, so if we call this energy operator, okay, then this is really not nice because I already used E. I mean, okay, I'm just gonna go with
N.
no, I'm not gonna go with N. No, not yet. So we have okay, so we have this. you recognize that this is basically the classical part. This is the classical part of what we have classically, right? This is kind of what we have classically. This is the energy, and this is the constant. Maybe it has relevance, maybe it does not. We don't know yet. Okay, but this is the energy operator that we're looking for. A single operator, and so supposedly this can tell us when this operates on the wave function. This can tell us the energy of the quantized field. Okay. Right. So, okay, now I'm gonna use do something else. So remember I said that there was no equivalent. There's no like a corresponding equations in the quantum realm for Maxwell's equation, right? Yes. So now we have the operator, and we can certainly define some kind of state. Okay, for the field. But what's the governing equation? What's the governing equation? Since the correspondence between field and the mechanical oscillator are so nicely mirror each other, people's first guess is just to use Schrödinger's equation and see if that works. Okay? So they also apply Schrödinger equation, which was used for matter. Now they are also using, by guessing, they're using Schrödinger equation for field or energy, pure energy. Okay? And when you go through Schrödinger equation and try to find the eigen energy of the system and blah blah blah, you will see that, and this is really cool. You will see that the energy is equal to h bar omega naught. The same omega naught here, but the h bar is introduced by the Schrödinger equation. If you notice, here I have tried in my whole derivation, I tried to avoid h bar. I did not bring h bar, right? Because I want you to know that where does h bar come in. And so all the canonical quantizations, all of this, quantization of the field operator and all this does not require h bar. Okay? The only assumption we really make is just this plane wave assumption. Okay, which is justifiable because we know pretty much any waveform, anything, any shape can be decomposed by Fourier transformation to the most fundamental unit of plane wave. So if we're able to quantize plane wave, then we can quantize any field. Okay, so we don't feel bad about bringing in the plane wave assumption. Okay, but so far there's no need for h bar, right? We have not used it, and we have no need for it until now. Now, because we're looking for a governing equation, okay, and there's really nothing we can use besides Schrödinger equation, so we just use it. And when we use Schrödinger equation and try to look for so you just basically follow the mathematics of a mechanical oscillator, right? And you try to find the eigenenergy of the system, right? Of the system, and then you will find that the eigenenergy is equal to h bar naught n 1/2, right? now you see, so if we follow that map, we see that this product here correspond to the number operator. Okay? And the number operator is give you how many elementary unit of excitation you have. In other words, the energy of an oscillator cannot increase continually. It increases in the discrete manner. That's the word quantization. Okay, it is in the oscillation amplitude per se. It is in the oscillation amplitude that is quantized. That becomes discrete. I'm talking about matter now. I'm talking about oscillators, mechanical oscillators. Of course, it's to describe this oscillator, you use a wave function, but that wave function is not discrete per se. It is continuous over the space. Okay, but it is the energy state of this thing or the oscillation is quantized. It increases in the discrete manner. That's the word quantum mean discreteness, small chunks. Okay, so we see that this increase in small chunks, n is an integer, n equal to 0, 1, 2, 3, 4. Okay, and n is basically a dagger times a. Okay, so if we do the same math for the electromagnetic field, then we will find that this also have the same form. Where's my red? Oh, it's gone out here. You also have the same form. Okay, and n, the operator of n give you number n, and the operator of n correspond to a dagger and a. Okay, and what is nice is this part, is this interesting part. Okay, here you see a fundamental unit of the field amplitude. Remember that field amplitude is associated with the field energy. If the energy has a fundamental discreteness, if it can only increase by at a fundamental unit, the amplitude also can only increase at a fundamental unit, right? And that fundamental unit is given, the correspondence is given here. Okay? Yeah? Which also means that this thing here, there's a fundamental importance here. When there is no excitation on the field, well, there is no excitation on the field. When the field is still, nobody disturb it, nothing, nobody touch it, right? Just like the ocean, nobody touch it, no wind, no nothing. Okay, there is this equation tells us there is still energy in this ground state when nobody touches it. And this correspondence tells us that energy, that fundamental energy that exists in the field when nobody touches it correspond to a fundamental oscillation amplitude, which means even nobody touches it, the field still oscillate. This is called the ground state motion. Or in a more vivid term, it's called vacuum fluctuation. Vacuum means no one is around. Nobody's disturbing this entity, this field entity. Nobody's touching it, but still by itself, okay, it fluctuates. Okay, it fluctuates, and this is that fluctuation corresponds to a ground state energy. Somebody also call it the 0 point energy. Okay, so 0 point energy, 0 point energy, or 0 point. So 0 point energy refers to this 1/2. 0 point fluctuation refers to this fundamental unit of field amplitude. Okay? 0 point energy, 0 point fluctuation, or vacuum energy, vacuum fluctuation. Okay? They all mean the same thing. Okay, maybe let me just write it. Yeah. Let me just circle it. And then yeah. Okay, so I just want to point out that, so this is what I want to, this is as far as the derivation go. I want to point out that the insight the quantization of the field brings us is that fields, in the absence of materials, absolutely nothing, in the absence of everything else, the fields still oscillate. The fields still fluctuate. And that has a physical consequence. This vacuum fluctuation is what is responsible for a number of physical effects, very well known physical effects, such as Casimir effect, lamp shift in atomic physics, and what else? And of course, there's also if you there's the anomalous for electrons. There is this anomaly in its magnetic moment. Okay, it's called G-2. G is the gyromagnetic ratio. According to the classical model, it's supposed to be 2. Okay, if electron does not have structures, if it's just an elementary point particle, it has no structure, it's supposed to be 2. But because of this vacuum fluctuations, you can imagine vacuum fluctuations as photons popping out of nothing and pop into its existence, disturb matter, play like boxing, hit the matter a few times, and then escape into the void, into nothingness. Okay, so the vacuum photons are like just bubble, it pops out from the vacuum, and after it interact with the electron for a while, it goes back to the vacuum. So for a very short time, it exists in the form of photons, and at that moment, it does have influence on matter. But after that time, it goes out. Okay, so it turns out electron is a very complex. It does not have a complex physical structure, not like neutrons or protons, which has smaller constituent particles, which are called quarks. Electrons does not. However, this constant interaction with the electromagnetic field feels like you have a layer of what would be it's like I would say it's like mochi, if you know what it is. Fishbowl, okay. Maybe fishbowl, like you have the stuffing, right? The stuffing is like the electron, and the crust, the outside crust, that's like the vacuum photon. Okay, so dynamically, so electron does have a dynamical structure, and that dynamical structure includes vacuums, vacuum photons. And if you take into account of this dynamical structures, then you can find that the electromagnetic moment, the general magnetic ratio is not exactly 2. It has at the fourth point after the decimal, the fourth digit after the decimal point, so it's 2.000. Then you have like a major volt value. And as a matter of fact, this whole business, after we quantize the field, we can use quantum language for both matter and field, right? So to account the complete quantum interaction, in the classical realm, it's called the interaction between matter and the field is called electrodynamics, classical electrodynamics. After we quantize both field and matter, now it's called quantum electrodynamics, QED. All right. So all this QED, all these vacuum effects, this vacuum dynamical structures, if you calculate this QED, if you run a QED calculation and take into account these dynamical structures, you'll find that the theory actually agree with the experiment to at least like 9 digits after 0, after the decimal point. Okay, so QED gives us a very accurate actually perhaps the most accurate prediction of physics theory. Give us the most accurate prediction from the physics theory, and that matches with the experiment. And all this accuracy are contribution from the vacuum field. Okay, this vacuum fluctuation is also called the vacuum field. When there's nothing, there's still something. Okay, kind of a philosophical. It's kind of philosophical, but it is real. All right. So I just want to point out this is very interesting. There's a very interesting dynamical aspect concerning this constant term, and that is the extra things the field condensation brings us. Right? This term we know from classical mechanics, and for all this derivation, we try to look for this term. But at the end, the condensation procedure gives us one extra term, and it turns out this extra term has physical consequences. It's just very small. Okay? All right. So I personally consider this incredibly interesting. Okay. All right. Next. So after we have quantized the field, I want to talk a little bit about how do we picture photons. We have used this word a lot, but what is a photon? Okay, what is a photon? To accurately, we also people always say photon is a fundamental excitation, right? You have heard that term. It's a fundamental unit of excitation for the field, right? Like, what exactly is it? To have a more accurate, a more scientific picture of the photon, I would suggest that we use the harmonic oscillator picture. And this is not just an ordinary harmonic oscillator. This is like the mode harmonic oscillator. Remember that matrix? Spring matrix I just drew, right? Okay, imagine we quantize all these springs, local springs, right? All of them are because all of them are in the harmonic potential, and they have their own energy states, right? Okay. Now, when they are connected, when they are coupled, it is the mode that matters. So they lose their individuality. They lose their individual identity, and then we go from single oscillator to like a oscillation of a single oscillator to the collective motion of all oscillators. So here, we also talk about quantization, but we're now talking about the mole oscillator. Okay, instead of the physical oscillator, the mole oscillator, and the mole oscillator, just like the physical oscillator, the individual oscillator, it also has energy states. Okay. It's just that this potential is not a real potential. This potential shape that we draw is just it is just like a metaphor. Sorry, this is just an analogy. There's no real potential for the mole oscillator, right? So if I have this as omega na, omega na, omega na, omega na, right? And there are 4 of them, so together they will give four mole frequency. 1, 2, 3, 4, right? Okay. So if I use mole oscillator number 1, yeah, then I can construct an equivalent picture for mole oscillator number 1 using that is oscillating at omega 1. Okay, and the spacing here is h bar omega 1. Yeah, but so the spacing is real, but this potential is kind of just an effective. It's not a real potential. Okay. All right. So when we talk about the field oscillator, it's the same thing as the mole oscillator. This harmonic potential that we have is kind of an effective potential. It's not real. Yeah. But nevertheless, the spacing is real. Okay. So if we talk about field oscillator and it's oscillating at omega naught, then this is the spacing is omega naught. Okay. And we can imagine this field oscillator by this picture. This is just the classical picture will suffice. Okay. So we have a field that oscillates. Now, when we are at the ground state, this is n equal to 0. When we are at the ground state, there is a corresponding energy of h bar omega 2 over h bar omega 0 not over 2, right? So this means and remember we talk about A have a fundamental unit. That means E and B also have a fundamental unit, right? So this fundamental fluctuation is there even when nothing is being perturbed. Okay, it's just that the field trajectory is not a very nice sinusoidal. Yeah. Are they supposed to? Oh, maybe they are. I don't know. Should they be in phase? Okay, if you say so. Okay, sure. Thanks. If this is the correct picture. Okay, so they oscillate, but just not following a very nice sinusoidal pattern. As a matter of fact, if you calculate E naught, okay, you'll find 0. And that makes sense because it's fluctuations. And if you calculate E squared, expectation of E squared is not 0. Okay, so that means it's basically it's like it's basically like a noise band. So this is the picture of the vacuum fluctuation, vacuum field. All right, we'll get to this later. But what I'm trying to say is this level, this energy level of field operator represent how strong your oscillation is, your oscillation amplitude. When you go up by one level, you oscillate a little bigger, a little stronger. Okay, but the increment is discrete. Okay, you cannot just say I wanna maybe have a 0.1 h bar omega naught increase in my field amplitude. You cannot do that. You must have an integer number of h bar omega. Okay, n equal to 2, n equal to 3, n equal to 4, so on and so forth. Yeah. So say this is, let me just say, again, this is still not an accurate picture, but just for the sake of explanation, let me just say this is n equal to 1, and this is n equal to 2. Okay, the amplitude is discrete. Okay, so what does photon mean? Photon photon means I have the number, let me put it, maybe I should say it this way. It is the number of photons that is meaningful. Okay, it is the number of photons that is meaningful. Later we'll come to this mental image of energy wave packet and it's moving. We'll come to that. But technically, it is the number of photons that is meaningful. And the number of photons represent the amplitude of your oscillation. If you are in a 2-photon state, then your field oscillation amplitude is larger than the n equal to 1 state. Okay, so it's in the field amplitude. So field number of photons correspond to the field amplitude. Okay, so I just want to get that straight. And so okay, so what about this picture of photons in the energy packet? So usually some people just picture it as this. This is a photon, okay? And if you are more sophisticated, you will add this oscillation in it, right? And this is probably the best mental image people can come up with for photon. Yeah. But I want to point out one thing. Number one is when we talk about photon, we always limit ourselves to the photon of a specific mode, right? Because photon is associated with this h bar naught excitation. So you need to say that what frequency this photon is. So photons belongs to photons. This NAND photon comes from the specific. It's associated. The photon is associated with. The term photon is associated with a specific frequency. That means all the photons we talk about technically are single mode photons. Single mode photons, okay? So this is implicit, but all the photons we talk about are single mode, and they are associated with one single frequency. And if it's associated with a single frequency, then you know that in time and space, the field oscillation is not localized, right? If the field is if the field oscillation is oscillated in the single photon state, okay, with that much amplitude, then this field is a single mode field, and if a single mode field is sine kx k naught x omega naught. This is a single mode field. It extends through all the space and time. Okay. This picture is this. It goes indefinitely in time and space. So that is different from the energy wave packet picture that we imagine. Okay. So is this mental picture wrong? Well, as an approximation, it is actually correct. But the technical description is actually very complex. Okay. So in classical electromagneticals, electromagnetism, a single mode wave is described by this, right? This is just a plain wave. Yep.
Would you mind using another color?
It's
orange, so you can see when it's so bright.
Oh, you don't like orange. Okay, sorry about that. I should refrain from using orange from now on.
Because it's not that problem.
Single mode.
For the figures, orange will it's not that problem.
Right. Yeah, I'm hopefully not color, but it's just so
I know it's too light.
color. Yeah, that because it's light.
Okay. Okay, from classical electromagnetism, we know single mode is described in a complex notation, exponential I, right? And this is basically just a number cosine k plus just 2 amplitude. And this is just a Fourier transform, okay? So I'm just writing this in a more elegant way. Okay, and then of course there is polarization. And that's all, pretty much, right? We have the amplitude, okay? We have the mole function, okay? And we have, how about green?
Yeah, I think it's good.
Green's okay? We have the oscillation. It has 3 parts, okay? And of course there is polarization. Okay, single mode. When we generalize to multimode, I'm talking about classical. Now, when we change to multimode, then we need to know what characterizes the mode in order to identify what modes are involved, right? And it turns out this, and that. The mode function, the oscillation frequency, the mode function, okay, exponential IKR, and the polarization, they characterize a mode. So if you have a multi-mode, then it is a sum, then it will be a sum of W, K, and E. Let me write S. Yeah.
For your oscillation form, you want to put them in different.
Huh? So what's that?
One is minus, one plus. So basically, we want to do that. And what you want to do?
What's the problem? I don't see it. This is a complex conjugate. Do I make a side round somewhere?
No.
Huh?
I just mean it's now we can consider it's just like one type oscillation. You can factor out that term out, and you don't need to consider it into your propagation.
Oh no! You cannot do that. Because that's only valid for standing wave. Oscillation typically is coupled with the spatial oscillation. Temporal oscillation is coupled with spatial oscillation. If you make them separate, make them independent, then that's only applied to standing wave. Okay. Yeah, but anyway, you cannot do it here. All right. So let me just use S. Let me just use S to characterize the polarization. Okay, because usually you have just 2 polarization, horizontal or vertical, and everything else is a linear combination of these 2, right? So S takes value of, you know, say +1, -1. One represent this and the other represent this. Okay, so just two values. So a multimode is a summation of this, and of all, and each single mode is characterized by W, omega, K, and S. Okay. So you have, and since omega is really just the norm, you can, omega is always related to K by this. So we don't really need to mark it. Okay. When we give K, when we give the complete K, we give omega too. It just, the reason I point this out is because you have the same omega, different K can share the same omega. So, and when they are, this here I more emphasize on the direction, and here I more emphasize on the amplitude of K. But just so you know, so this is like to be very thorough. And if I just want to make things easier, I go with just K and S. Okay. And I have here every one of them KS0. KS0. And even the polarization, I can just put KS. Okay, so everything has this tag K and X and S. Okay. All right, so this is multimode, right? So this is classical. Now, when we do quantum, right? At a single mode level, which is what we did earlier, at a single mode level, we have said this operator really, what does this operator mean? It's really just an amplitude. Okay, so the operator is, it is the amplitude being quantized. So we put an operator right next to this thing. Okay, so this is quantum. And when we have a multimode, it's pretty simple. Just put K, S, like that. K, S. Yep. Okay, why do I say this? The reason I say this is because in order to have, so what we picture here, whether it is this or this both are associated with the mode function. Okay? So whether you want to have a waveform like this or a waveform like this, you must have a wave function that corresponds to this. This is a single mode wave function, mode function, and this is a multi-mode mode function. Only through different components of only through a summation of plane wave you can have such a waveform, and this is a single. Okay. So in order to have an image like this must be a multi-mode. Okay, so let me just say this must be a multi-mode. And this is just by Fourier transform. And this is a single mode. Single mode. Okay? Okay. Now, where does the photon come in, right? I said photon is really represent the magnitude, is basically the magnitude of your oscillation amplitude, right? Saying that it is an excitation is the same as saying that it represents the magnitude of your oscillation. or the oscillation amplitude. So it is here that is quantized. Okay, so that means you have large oscillation or small oscillation. If you have a single photon, you have a small oscillation. If you have a large photon, you have a large oscillation. Qualitatively, it works this way. Okay, so so if I would draw a photon distribution, okay, so this is n, this is Pn, and this is 0, 1, 2, 3, 4, right? I could have say 3. I can have all my a field state equal to 3. Okay, so sorry. So the field, because the Hamiltonian is the constant motion, and the eigenstate, the constant motion, the eigenstate correspond to that constant motion is the photon number, okay, excitation number. So this characterizes our field state. So we will use n for our field state. Okay. So if you have a field state of 3, then that means all your probabilities are on n equal to 3. And whenever you look at the field, you will find it oscillates with this much amplitude, 100%. Okay, but it is, I mean, it's quantum mechanics, so you're allowed to have different distributions, right? You could have 2 of them. Okay, you can even have 3 of them, or even better, a number of them, a kind of a distribution. So you can have a width. Okay, and this width, this is characterized by a width in the photon number, and this distribution is characterized by an average photon number. Yeah, so these are allowed. This amplitude superposition are allowed. And when you have amplitude superposition, it is the single. When you have amplitude superposition, your waveform changes. Okay. The one that we are most familiar with, the sinusoidal oscillation, that actually correspond. So this sinusoidal oscillation or actually correspond to a distribution of a distribution with non-zero width, and this is called the Poisson distribution. A French physicist, Poisson's distribution. Okay, and Poisson distribution is it's A alpha n over n factorial n. Okay, so this is Poisson distribution. This is the Pn. It is characterized by a single parameter alpha, and this single parameter give you the average photon position and the width. Okay, and we call the field that has this Poisson distribution the coherent state. Okay, coherent state. We just give it a name called coherent state. Okay, so this is sorry, this is supposed to be square. Okay, so this is the probability amplitude. Yeah. So turns out that this distribution that follows the Poisson if you have a photon distribution that follows Poisson distribution, then your temporal evolution will mimic a sinusoidal trajectory. And that is very close to what we have as a plane wave in classical mechanics, in classical electrodynamics, right? And that's why we call it coherent state, because it oscillates coherently for a long time. Okay, but there's a one important difference, that even this bears a quantum feature, although that is kind of hidden. Okay, so this oscillation is actually the average E. But if you calculate the E, so this is the average E. But if you calculate the E square, or the E distributions, let me just write E distributions, okay? You will find this is non-zero. That means you have a little bit fluctuations. So there is an envelope of fluctuations around your classical trajectory. Okay? And these little fluctuations here, that's the quantum feature. That's due to the vacuum field. Okay? And this quantum feature is used actually in quantum communications as a resource for coding this width. Yeah. All right. So if you have a large alpha, you have a large average photon number, right? And this distribution moves to a higher number, then you have a large amplitude. Okay? But if you have a small alpha, this will approach zero. This will approach zero. And the width will be small too. Okay? And the width will be small too, and it will be very close to 1. And you can imagine that this is the distance between this and 0 is very, very small. Okay? And if you go even a little bit even lower, if you go to like absolutely 0 for alpha, then you have the vacuum state. So increasing alpha, you are increasing from the vacuum state, carry the same width, but that vacuum state band just kind of start to oscillate with a certain offset from 0. Okay? Okay, so that is how the field look like given a particular photon distribution. When we have 3, the photon distribution is not like a continuous. It's the field is in the at a single time, the field is in the superposition of three values. And it's all very fascinating, okay? But we don't have time to talk about that. I just want to let you know that photon distribution is the quantum nature of the quantized field. A classical field does not have a discreteness in the amplitude, and it does not have a superposition in the amplitude. I mean, it doesn't make sense to have a superposition in the amplitude. If you can have a continuous value, then you can just take any value. Why a superposition, right? All right, so that's for one single state. Now, to do this, okay, to do this, you must first have you must have in the single mode Poisson distribution, right? To have this sinusoidal oscillation for each mode. And then for multi-mode, you have all the modes have different. All the modes. Imagine this sinusoidal oscillation is for all the involved modes, and then under that framework, you can combine all the sinusoidal into this wave packet. Okay. So this wave packet picture is really this wave packet picture for a photon, physically really correspond to multimode, many frequencies needs to be involved, and all modes needs to be in Poisson distribution. Almost must be in coherent state. Coherent state means Poisson distribution in the photon statistics. Okay, in the photon statistics. Okay, you must have this in order to have this waveform. And then now it is the matter of this amplitude, right? And you can imagine that if I have a large oscillation for each mode, then it's likely that when they constructively interfere at the point of the highest point, so this highest point corresponds to the maximum amplitude of all my oscillations, all my modes. So that means, so this amplitude here basically correspond to a distribution of n. Yeah. If for each constituent mode I have a low n, then this will be a small value. If for each, but the waveform still looks the same. Okay, this is a temporal waveform. Okay, so that means this single photon really is a very low averaged. So this is equal to 1. You understand what this means? It means this n is so low for each mode. Okay, they're almost 0, like maybe 0.2, 0.4, 0.7. They're so low that all of them together. So a photon means this is only this has this one photon only makes sense in the statistical sense.
You said that's also the amplitude, right?
Huh?
So the amplitude is 1.
Yes. So this one photon, this one only makes sense in the average sense, in the statistical sense. Okay, so that means all the constituent, all the mode for, so this is mode. Okay, so n ks. So all the constituent mode average photon number must be smaller than 1. If all its constituent is smaller than 1, this one photon is not really, it's really in the superposition of all of them. Okay, so this is really, this picture is, this really, it is very different from this photon that we have derived from field condensation. It actually, if we want to use that language, it actually, this represents a very complex picture. Okay, you have this, all three of this. Okay. Okay, so the last thing I want to say is, now we know that the this is the last slide. So we're done with the field quantization. Okay. The last thing I want to say is, so you see, after we quantize the field, the quantum field still have the same mole function as the classical field, still have the same oscillation as the classical field, still have the same polarization as the classical field. It is really just the amplitude that is being quantized. So the distribution of that superposition of amplitudes, that is what zero, 1, 2, 3, 4. Okay. This distribution is what characterized one field state from the other. Okay. And so this is a Poisson distribution, right? So this is alpha, and this is 2. Now, let's talk about measurement. This and this both share the same mole function. It's just the amplitude is different, right? They both share the same mole function. So if I use an interferometric experiment, if I use an interferometric measurement, for example, I look at the fringes of my beam. So I put my beam into a Mach Zehnder interferometer. Okay, I put my beam through a Mach Zehnder interferometer, and I want to know if it is in a coherent state or if it's in a 2-photon state. Can I do that? Can this measurement tells me any information? Can this measurement distinguish between this and this? Can the contrast here show me the difference between this and this? Cannot. It cannot. Okay, because they share the same mole function. Okay, and what is interfering here is the mole function being interfered.
But the intensity of the interference pattern.
Yeah, but that's not a qualitative difference. That's a quantitative. And you, like, for an experimentalist, what you will want to look for is a qualitative, is a smoking gun that tells this is an orange, this is an apple. Okay, it's not like this is 0.2 higher than this value. Yeah. Okay. So this kind of intermetric measurement cannot tell this apart. It takes and like we said before, the coherence, the fringe that is measured here, the fundamental reason why this cannot be this interferometric measurement. Interferometric measurement. The fundamental reason why this cannot tell this apart is because the interferometric measurement is yeah, if you remember, we talked about optical coherence. Right? So classically, it is gamma 1. But quantum mechanically, it is G1. And G1 is basically the same as that. You just change this to an operator. So this is dagger. Okay. now we have defined n in relation to a, and a is, we know how a is related to e and b. I think this is not hard, right? We can do this kind of calculation. All right, so classically, what we measure in an interferometric measure is this, the first order coherence function. Okay, and when we switch to quantum language, it carries the same form, functional form. This becomes operators, and that's all. And instead of average here, we have ensemble average plus time average. Okay, but fundamentally, so this basically means E operate on, right? E operate on the field state, and E is a combination of raising and lowering operator A. We call this raising operator, this lowering operator. The physical meaning is that this is electromagnetic field operator, but mathematically we call it raising and lowering operator. Okay. So you see that when this operate on the field, when this operator inquire the field, it does not it cannot get any information concerning the photon distribution because we don't have a number operator. Okay, we don't have a number operator. It is we need to have an number operator in order to tell which photon distribution we have. So in order to have a number operator, we need to have products of A and A dagger. Okay, so that brings us to this. That's why it brings us to the second order, to consider the second order coherence function. Okay, and the second order coherence function is not like a hierarchy. It just means that this inquire a different information from the field. This inquire amplitude, not really amplitude, but yeah, I don't know. But this is I. And G2 is the same. Now you see here we have 2E, E squared, E times E. So we have A times A, and this gives us the cross term, the number operators. This is the number operator, right? And this is 1 plus number operator. Okay? So this is the reason why we need to use, and what corresponds to, so the interferometric measurement corresponds to the first order coherence function. What corresponds to the second order coherence function is called the correlation measurement. We talked about this in the Humphrey-Brown, in our discussions on Humphrey-Brown twist experiment, correlation measurement. Okay, that's why we need to use to enable to see the quantum nature or the particle nature of field. We need to inquire its photon statistics. To inquire photon statistics, we need to use a correlation measurement, because only in the correlation measurement we have the photon operator that it can be used to inquire information about the photon statistics from the field state. Okay, so that's very mouthful, but all this discussion just to justify for you why we're using correlation measurement for quantum optics experiment instead of the interferometric measurement. Okay. All right. So that's all. That's all I want to talk about today. And of course, quantum coherence. Oh, yeah. Last thing. The interferometric measurement. So it is a correlation measurement. And as we talked about before, in previous lecture, this one, so C, or let me just write G2, okay? We call it G2, depending on what language you use, okay, but let's call it G2. One means uncorrelated. Okay? This means correlated. Larger than 1 means correlated. Okay, so G2 and G2 equal to 1 is uncorrelated. G2 larger than 1 is correlated. Yeah, or positively correlated. Yes? This is the realm of classical. This is described by the classical physics. Okay? In other words, the non-classical regime, G2 smaller than 1, this is non-classical. Thus, it is quantum. Okay? So, no, we cannot really give you the quantum, the photon statistics, but we can tell you which light, whether the light is a classical light or a non-classical light, a quantum light. We can give you a yes or no answer. Okay, that's what the correlation measurement can do for you. And I usually give you this dip. Okay, and this corresponds to this dip here, smaller than 1. That corresponds to a quantum feature, and if this dip disappear, that means your quantum coherence for the energy is gone. Okay? That means the quantum coherence for energy is gone. Remember, the quantum coherence for energy has a particle nature. The quantum coherence for matter has a wave nature, right? So okay, so anyway, that's all I want to say. All right, cool. So
you said like the interferometric method we cannot distinguish. So what's the method we use? Like a single photon detector?
Say again?
Or you said in the interferometric method we cannot distinguish between them.
Right.
So the method we
use
is like single photon detector.
No, it is not the single photon detector per se. It is the correlation measurement.
Yeah.
And the detector that we use it's called single photon detector, but it is really not a single photon detector. It is just an avalanche detector. Avalanche detector means it's very sensitive to small number of photon flux. Okay. It cannot tell if you have a single photon or a two photon state or a three photon state hits. You cannot tell that. It's just that when the field when your intensity in the beam is very low, you naturally need to go to a more and more sensitive detector, and that's all. This detector is fundamentally the same as the other detector that we use for the other photodiodes that we use for normal light. Okay, it is the correlation measurement from the signals that tells us the quantum nature of the light. Okay, yeah, so it's really not a detector. I can use just the photodiode detector if my beam intensity beam flux is strong enough. If you have a strong flux, does that mean it's not quantum? No. If you have a weak low flux, does that mean it is quantum? No. Okay. Okay. So we need to distinguish between the difference between average value of 1 versus n equal to 1. This is a quantum state. This is a quantum light. Single photon state. This could mean that it is a coherent state, just with a low alpha. This could mean this is a squeezed state. Okay? Some people call squeezed state non-classical or quantum. It is not. Okay? Because if you use in the quantum mechanics, in the quantum optics textbook, we typically use Wigner function. When you, the negativity of in the Wigner functions, or even this correlation measurement, to distinguish what is G2, to distinguish what is classical and what is quantum. Okay, and squeezed state fail both tests. Okay, as a matter of fact, I can produce squeezed state just from in the classical in the framework of classical electromagnetism. I can produce the trajectory of the squeeze state from classical electromagnetism using parametric amplification. Okay, so anyway, that is beside the point. What I'm trying to say is it is very important to know the difference between these two. This could mean quantum, yes, sure, because here we also have an average photon number of 1, right? This could mean photon or classical. This is definitely quantum. Okay, so a lot of people mistakenly, wrongly take this as the quantum light, a low intensity light as a quantum light. That's wrong. That's not true. Okay. All right. Good. Let's go to the quiz. We have very short quiz questions for you guys today, and I hope you can all win. Okay. Shoot. All right, this is really simple. What G2 value is classically for beaten and would indicate
and can serve as an indication for quantum light. Is laser a quantum light source? Okay. So for the first one, larger than 1, smaller than 1. For the first question, larger than 1, smaller than 1. Come on, let's go. Earn your points. I'm giving you this point for free. Smaller than 1. Okay, let's just do a very short discussion for the sake of it. Okay, you 3 will be one group and you 2 will be one group. And start with always, you're wrong.
You're right.
You're wrong.
He basically said that
I think you're wrong. Explain to me why.
if it's less than one, quantum.
But why?
You're wrong. Please explain to me what is that?
You said it.
I think it's true.
No, you're wrong.
Why?
Yeah, I think you're wrong. So you should
You're
explain.
wrong.
I'm wrong.
But you choose.
You're wrong because it should be bigger. But
Yeah,
why couldn't it be bigger instead?
So why you to use three?
No, that is a rhetorical question. No, just answer the question. Just fight your answer.
Mm-hmm.
1 minute.
I say you are wrong, so my answer.
Mm-hmm. Okay, interesting.
Make a story.
What about the noise you mentioned? What is the
Yeah, you
effect
get
of
from
the
it
noise?
that.
Okay, should I flip this sign or be?
So you have to be fair, right? You have to be fair. So what
Okay.
is really like it take if to
Basically the
Okay, thumbs up. Okay,
Yeah.
thumbs up.
lose
Anybody feel now more doubtful of their own answer after this round of discussion? Anybody want to switch side?
greater than one.
Hey, guys, anybody want to switch side? Okay, that's without further ado. Yes, this is the correct answer, but I don't think everybody knows why. Okay, everybody knows this is the right answer, but not everybody knows why. I overheard some of you say mention about vacuum photons, right? Vacuum. I just wanna make one more remark on vacuum. The vacuum fluctuation, also called the photon that is associated with vacuum fluctuation, is also called the virtual photon. They are, for a brief moment, they are indistinguishable from the regular photons. The fundamental nature of it is not different from the regular photons. It is the lifetime. The real photons are the photons that exist indefinitely until it gets absorbed. That's the photon we talk about typically. The virtual photons are photons that pops out of a vacuum for a very short time, live for a short time, and for that short moment of time, it will function just as the real photons. There's no difference. But then you will go back to the vacuum after a short moment. So the lifetime of it is very short. That's the vacuum photon.
Okay, therefore, in average, temporarily, it can have an effect, but in average, it cannot have an observable effect. All those are shift or the anomaly in the those are the transient kind of a transient effect. But since it keep happening, it kind of have a lasting effect, but first rather small. All right. So I just want to make the additional remark on partial photons. Okay, second question. So this is everybody got this right. So Tom, Simon, Phoenix, and okay. Is laser a quantum light source? This is a little harder question to answer. So here probably we have even a more interesting debate.
The light is quantum or the
It's
laser
laser, the laser we use in the lab, okay? Zzz, zzz.
the light it produces quantum or not, right?
Yes. Can the laser, or let me just say, can Heine laser? This is Heine laser. We have Heine laser. We can also have the semiconductor laser, right? It doesn't matter. Can any of them be considered a quantum light source? If yes, why? If no, why? Okay? Please pick your answer.
There can be some weird kind of
You try to say that to your friends. Okay. I think I have already explained every single words here. So it requires no further. So everybody want to vote for no? Okay. Then in this case, I will have you and maybe you two will discuss, and you three will discuss. Okay? Please. You're wrong. You're definitely wrong. Start with that. And then you debate.
I think you're wrong.
Thank you.
Why do you think?
Love this guy. He just stick with my protocol. Yes. My script.
laser always make coherent lights which are classical. Yeah, but the production of the light is a quantum mechanical process. So the light is produced.
Okay, you said it was a coherent light, right? Isn't the coherent light like quantized energy level?
No.
Why?
No.
Coherence can be, you want to mention, can you put it on the
Yeah, if everything is the same, you shouldn't be quantized.
Like everything has a quantum nature, but if there is more amount of that can classical. Quantum nature is like the information should be like a particular kind.
What's your definition of a
be like
quantum light
some
source?
principles will be applied. But when there is a lot
Okay.
of them, then it's like classical. Like coherent light is not that. So G2 will be always the one.
Yeah.
You need to make some other things
In
to
the
make it
quantum light source, you have
the light it produces itself is
you can have
classical, but
quantum
you can make
coherence
it
between
quantum
photons,
using
right?
different processes.
Which processes?
Means making them entangled and all those things. You do those things like after the production of light, you can make quantum light from that. But the light is produced itself. That's what I
That's not the type of light the generates.
Yeah, there's basically.
Now, of course, you can still use the laser light to demonstrate.
Okay.
In terms of the
10 seconds.
and Fox state also described in the state frequency. So that's
The
possible,
laser just
but
creates
Fox
classic
state and
coherent
state,
light, right?
they're different. But Fox state
The laser
and
creates
So
coherent light,
quantum
but classically coherent light.
it's like this. But coherent state from
Hands up. Hands up. Go back to your position. Thank you. Anybody want to switch side after the very intense discussion? All right. Next round, I'll have you two discuss with each other, and you will discuss with Tom, and I will be your eighth person because David is not here. So I will discuss with Phoenix. Come. I'll be your sounding board. Okay? Come on, come here. Come here. This is very crowded. We have a very high density of people here. Come here, spread out. Okay, let's start. You're wrong. You are wrong.
I will hear your argument first.
I think because
But
we're talking about the
Laser is a quantum light source. You're wrong. No. You explain. You need to defend your answer.
But I mean, mostly the laser has the classical coherence.
you can make that light
I think if the photons it produces, they are classically coherent. Like if you measure
Don't cry.
and
How do a laser produce light?
It uses
It's okay to be wrong.
quantized
Just switch
energy
side.
levels, yes.
Next
But I don't think that's the
Next round.
definition of
What we use
like
Quantum process, right?
yeah, it uses a quantum process.
Yeah.
But I think we're talking about the source, like the light it produces.
basically describe it
But of course,
mechanism.
Fox
If
state.
the definition is if it uses the quantized energy levels, whatnot, then my answer would be yes.
Yeah, exactly. See, I think you're
So
wrong.
for
Yeah, but why are you standing here then?
because Fox state is very same for
So
the
you can
number
have
of
like the
photons.
quantized energy
So we
levels,
can like
and the source is a quantum source, right?
Yeah.
I don't really.
Why mention Fox
It's a
state?
quantum source.
Yeah.
Is laser a Fox state?
Yeah.
Is laser
I think
produce?
that's the
Does
definition
laser
that
produce
we
a Fox
should
state?
ask you to
no
investigate.
for single photon.
Because I
Laser
think
is
we
coherent state.
agree
Laser
that
is coherent state.
Because
it
light
uses
sound
very
they have
Okay, so is coherent state a quantum
in
light?
the emission,
No.
etc.
Why?
Which is very quantum,
because
but
coherent
light-
state is based on the
But I think the light it
Before
creates.
We had to
Poisson
see-
distribution.
Yeah.
And
That
it's
is something
classical.
that-
And why cannot? Why Poisson distribution has to be classical?
Is laser light
Why? I mean,
quantum
why
light?
any distribution has to be
Light
classical?
source.
We can see by Wigner functions that there will be negative.
Oh yeah, it's a source.
The teacher never says Poisson state is the classical distribution.
Is laser a quantum light source? But it could still be his.
Then it's quantum. As far as that.
You can also have a gamma distribution. Is gamma distribution
You're
a
talking
better
about the light of the
distribution?
machine.
And it's that's quantum?
So give us if it's a quantum light source.
I don't see
Yeah,
why
but
it has
this
to
is not-
do with the distribution.
But I think it's in one the lesson you mentioned about like single
Laser, only type of
Yeah,
laser.
but this does not produce a single photon, does it?
Every laser is
Yeah,
This produce, like you say, a coherent state.
Random correlation inversion.
Does
So you need to describe more about your quantum light source. What
no
do you
no no no
mean?
no. So I just don't understand why coherent state has to be coherent.
Yeah.
Classical. I mean, why is this worse than Fox state in terms of quantumness? Why is coherent state worse than
But I
Fox
think
state?
the light it produces is classically coherent. We're talking about quantum coherence, what we did like in the lecture yesterday, right? We have more.
See, you're wrong. You should
different
change
types
to
of
this
coherence,
answer.
but it's not really-
Yes.
Yeah, I mean, you need a different type of entanglement.
but-
somewhere.
you need to go back to
Would you agree?
If there is some entanglement, then
Your
we
question.
get less than one.
I think you need to
They put it the state.
explain more about your question. What do you mean about quantum light source?
Quantum light source means there is some kind of measurement that you can tell.
Is quantum or classical?
Yeah.
Okay.
So when you talk
So
about
for-
quantum light source, you always want to think about what kind of measurement you want to do.
I know you
For
guys is
example,
talking about the
in
Yeah.
light
I can
the
use,
machine produces not machines are prime power.
to say that one is classical or quantum, right?
Yeah.
So if I use the coherence,
Coherence?
But it's
so
no
like I use
Ah.
laser.
Laser, yes.
Okay. So the
coherent light is
uh
So
it's
property.
like
If you do like
the photon normally it will like function, right? If right, so it will go in group. And
Okay.
and for example, in the setup,
The regular light is just coherent light.
I have
It doesn't
say
have
the
something
newsletter,
quantum.
and I can separate that to be
Yesterday we
integrated.
also
So
talking about it, like if you try to apply the quantum description to laser light, it becomes nothing, right? Or not really, but a little bit. Something like that.
See, you want to switch to
no,
this side?
no.
Yes, yes.
I'm seeing the right side.
You are wrong. You are wrong. You're all wrong.
Let me see how can
Oh man. Okay, thumbs up. All right. Do we need one more round? Who wants to pair with me? Anybody want to switch side? No? Okay. Ah, man. So boring. All right. Because we are running out of time. Yeah, this is the correct answer. ETSPM. Okay? Quantum light source means that you have to have some kind of measurement to tell whether this has a quantum behavior or this doesn't have a quantum behavior. That's the only way to tell whether something is a quantum light source or not. The measurement that we will use, like we just mentioned, has to be sensitive to photon statistics. Okay? And so different photon statistics can give you different G2 values. The G2 value that is allowed to occur within classical physics is G2 larger or equal to 1. Okay? So whatever photon distribution that give you a G2 that is larger or equal to 1, that is considered classical light. It does not mean it doesn't have coherence. Actually, that's why here we need to distinguish between quantum coherence and optical coherence, because you can be a classical light still with optical coherence, or you can be a quantum light and still with optical coherence. What optical coherence pertains to the mode function. Yeah, okay, because it's like the interferometric, is an interferometric feature, and the interferometric features probe only the mode function. Yeah, so no, laser is not like a quantum light source. Only those light that produce G2 less than 1, that is quantum light source. Okay, cool. That's all for today. Thank you very much for your incredible patience. And I'm glad everybody get a point. And otherwise, I feel bad after keeping you here for so long. Like, this lecture is incredibly long. All right, let me post it.